we started 1.2 last time, finding limits graphically and numerically. And there's sort of a third part of this section that's not in the title. And the third part has to do with finding limits and proving that they're really the limit. So what we have been doing so far is, it's kind of like eyeballing it, approximating, saying it looks like it's really getting close to, right? This is a little bit of hand waving, right? Hand waving is something that we don't really say that we've proved, but we feel pretty confident in it, right? We feel pretty good about the fact that it looks like it really is, approaching 2 or whatever the number is. All right, so what we're going to do today is we're going to actually do something that's going to look more like a proof, but it's not going to look like proofs if you did proofs in geometry. They're going to be paragraphs. So let me develop what this looks like first with this one. Okay, so we're going to consider a function, f of x equals 5x plus 2. What does this look like? It's a line. It's a line with slope 5 and y-intercept 2, right? Okay. We're going to consider finding the limit of 5x plus 2 as x approaches 3. I know we haven't gotten to section 1.3 yet, and that's fine, but I'm just going to tell you right now the limit's 17, okay? So we'll talk in section 1.3 about how we can find that limit very quickly, but the limit is 17. So if we were to do it numerically, or if we were to approximate with a graph, like we've already talked about in this section, it would intuitively make sense. It would make sense to us that it's getting really close to 17. In fact, if you put 3 in for x, it's actually equal to 17, right? So this seems quite reasonable. But the description is imprecise. And so we're going to take a look at the graph. Okay, so we're going to start by drawing the graph. We've already described what the graph actually looks like, at least approximately so. It crosses, and it's just going to be a little bit of a sketch kind of graph, but it'll be good enough. It crosses at 2, and it has a slope of 5. So here's 2, and it has a slope of 5. So the idea is that if we get really close to any particular y value, in particular, we looked at 3. Let me put it there. We'll call this 17. Again, it's not to scale. My drawing's not to scale, and it doesn't need to be. But if I take a look at the limit as x approaches 3, I'm told it's 17, and there's a point right here that's at 317. Okay? So if the limit's really 17, which we've been told that it is, I should be able to create this sort of small, we call it a neighborhood, around 17. It's really close to 17. And as long as I'm really close to 17, I'm also going to be really close to 3. Does that make sense? All right, those y values and those x values, they go together. Now, it doesn't mean that the really close to is in the same scale. That doesn't have to be the case. I might need to be closer to 3 than I am to 17 or vice versa. But I somehow need to be close. Okay, the description is close. So we're going to firm it up a little bit with the formal definition of limit. Is it my next page? Oh, it's in the bottom. Yeah, so give me a couple more seconds there. We'll get to the formal ones at the bottom of the page. So let's say that we wanted to make sure that the function value and the limit of that function as x approaches 3 are close to one another. That's what we just said. Perhaps we want them to only differ by 1 unit. So if so, the question is how close of an x value to x equal 3 would be required to make sure that we're as close to 17 as 1. Okay, so in other words, over here in my picture, I want these numbers over here to be 16 and 18. I want to be within 1 of 17. The question is, how close do I need to be to 3 to make sure that that really happens? Okay, does everybody understand what I'm saying? Okay, so over here, what we want is we want our function, which was 5x plus 2, and our y value of 17 to be really close together. And you may remember that absolute value just finds the distance between things. So this is the distance between our function, like our graph, right, and the y value 17. That's what this is representing. And we want them to be no more than 1 apart. Is that all right? So we're trying to then figure out what in the world or how far apart can x be from 3, right? So just like the same definition for the y values, these are both y values, right? These are both y values. Then this is the x value, and it's supposed to be close to the x value of 3. These are two x values down here, an arbitrary x and x equal 3. So here's the way that this works. We're going to take that inequality that's written right here, and we're going to solve it. Okay, so this is an algebra concept. It might not be a concept you've seen in quite some time. Typically, I think it's algebra 2. It might be algebra 1. Sometimes the lines blur between those two things. But we're going to take this and we're going to solve it. So the first thing we're going to do is we're going to recognize that the parentheses around the 5x plus 2 are sort of irrelevant, right? I mean, I don't need to do anything to the 5x plus 2 to just remove the parentheses, so I can, which means I can combine the 2 and the 17. So I can actually change this into 5x and then minus 15. Okay, is everybody good with that? Okay. At this point, what will always happen as you're moving forward with these is you're going to notice that there's some way that you can simplify what's inside, or factor, we'll say it that way, factor what's inside those absolute values. What value can I factor out of each piece that's inside my absolute values? 5. Okay, so I'm going to rewrite this, and I'm going to take a couple of steps just because in a future problem it's going to be more necessary to see it. I'm going to put a 5 right here, and I'm going to put the x minus 3 right here. And I'm going to recognize that this is the same as the absolute value of 5 and the absolute value of x minus 3. I know that sort of feels funny because 5 is already positive. The reason I mention it is because if we had a negative number right here, we'd have to do the absolute value. Okay? So I'm putting it there on purpose so that when you encounter something that's got a negative 3 or negative 7 or negative 5, you remember you still have to take the absolute value. So this becomes a 5 out here in front. And you'll notice that in that factoring, it'll always happen this way, that in that factoring, the piece that we're wanting over here is going to show up. Okay, that's always going to happen. Okay, so if our goal is to get x minus 3 in the absolute values alone, we would then need to divide by the 5, right? So we're going to divide by 5 to the other side. And what we're going to get is that the x minus 5 is less than x minus 3 is less than 1/5. So on the y-axis, if I'm within 1 of 17, I can't be within 1 of 3. That's not close enough. So over here, these values actually can only be 1/5 away from 3. So in a very real sense, this is 3 1/5, and this is 2 4/5. It has to be tighter around the x-axis on this particular equation than it is on the y-axis. Why in this equation is that happening? Because the slope's 5, right? The slope's really steep. So every x value that I change causes a bigger change in y than it did in x. Does that make sense? Okay, so if my slope had been, 1/5, the opposite would be happening, yeah? Okay, so it depends on what the slope is. So what we just did very precisely for being 1 away from the 17 can be done arbitrarily by using an epsilon. We chose 1 kind of arbitrarily. I just picked it. We could have chosen any value there. So in general, we're not going to choose 1. We're going to choose an arbitrary or a variable value, epsilon. Epsilon's a positive number. It has to represent a distance, so it has to be positive. So in the same way that we did this before, we're going to do this again. We're just going to have epsilon in the place of where we had a 1. So this 5x plus 2 can still have minus the 17, but it's less than epsilon. I can still combine it, 5x minus 15. I can still bring out the 5. And I can still divide by the 5. So over here, instead of it saying x minus 3 is less than 1/5, it's going to say x minus 3 is less than epsilon over 5. And the name that we're going to give this quantity, whatever ends up being, is the Greek letter delta. That's a lowercase delta, so if you've seen like sororities, fraternities, and use a delta, that's why it looks different. That's the lowercase delta. Okay, so these kinds of proofs are often called epsilon delta proofs because we're going to have epsilons and deltas in them. That's what they're going to be called. But what they're really doing is they're really finding what we would call the precise definition of limit. And that leads us to exactly the precise definition of limit. I want you to circle this, star this, mark it up in red, highlight it, whatever it takes. Because I'm going to tell you that you're going to memorize this for the first test. And even as I tell you that today, half of you are going to ignore me and half of you aren't going to do it anyway. And you're going to miss the points and you're going to go into the test knowing you're going to miss them. And that's really unfortunate. Because at this point, y'all know how to memorize. You've memorized things for 12 plus years, easy for school. You can memorize this, okay? So if you're a slow memorizer, start working on it now. You're going to have to memorize this, and it's going to be asked to write it down exactly like this is on the test. The precise definition of limit says, let f be a function defined on an open interval containing c. Okay, so f was our function 5x plus 2. C was our x value of 3 just a moment ago. It says, but except possibly at 3. Except possibly at c. The reason it says that is because you could have an open circle in the graph and this would still work. Okay, because you have a hole. You could have a hole in the graph and it would still work. We're going to let L be a real number. The statement, the limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, okay, that's the epsilon we just did in the problem before, there will be a corresponding delta. That's what we figured out was epsilon over 5, such that if 0 is less than x minus c is less than delta, then f of x minus L is less than epsilon. Now I'm going to write down what we just did with this specifically for the function we did. We found that delta was epsilon over 5. And we found that if we were within epsilon over 5 of the value 3, then we were guaranteed to have our function be within epsilon of 17. This is exactly what we did. We just did it with concrete equation, y equal f of x, or f of x equals 5x minus 2, and a concrete value for c, namely 3. I will say memorizing is always easier to do if you understand what it is you're memorizing. So if you can digest this as you're working through and remember what it is you're doing with all the pieces, the memorizing for this is going to be a lot easier. Okay, so we need to do some examples, right? We need to see how it works. We've done one example already, the 5x minus 2 and with the 17 and the 3. We're going to do this one. The directions say, on mine say find the limit. I've actually given the limit on my screen. I think this is to save time. Let me remind you that to find the limit, you have two options right now in section 1.2. You can use a table or you can use a graph. And so if you're asked to find them, let me see if you're asked to. I think you are. I'll show you the first one, how we find it. One way anyway, a reminder for that. But I think for the sake of moving forward more quickly is why I put them in. So to find the limit, we'll do a table for the first one anyway. So the table looked like this. We have our x values and we have our y values. The x value needs to get really close to the x value of -2. So we do values that are slightly smaller than -2. That's actually -2.1, -2.01, and -2.001. And I'll do another table over here. I'll minimize these tables when I'm done because I need some space later, and we will do a slightly bigger than -2, which would be -1.9, -1.99, and -1.999. Take your calculator. You'll put the equation 3x plus 2 into y equals. And you'll go into your table. Those of you who were not here last time, that would be Kingston and Candry. Is that true? Just those two of you? You don't have one with you. You do. Let's just change it to one real quick because I had them set it up. Did you put y equals yet?
Oh, yeah.
Okay, yours is set up. Good. Okay, so is everybody set up where you can still put values in x equals? Okay, great. So you're going to put these values in, -2.1, -2.01, -2.001, -1.9, -1.99, and -1.999. And we can see in the table that this creates that we have -4.3, -4. Hang on. Oh, I've got a typo in something. Just a second. There we go. 0.3 and -4.003. And on the flip side, I have -3.7, -3.97, and -3.997. Do yours look like that as well? Okay. And if we go down the tables, both of them, what y value are we getting close to? 4. Yeah, -4. So my limit L that we keep talking about here is -4. So that's why this is showing up here as -4. We will have a way to do this even easier inside of section 1.3. But for right now, tables are a good option. If you want to use a graph, you're welcome to do that. I'll show the graph one as the next problem, okay? So on the next one, we'll do a graph. This one, I proved it, if you will, or I justified it at least with tables. Okay, everybody good with that? I need more space. Okay, so once you know the limit value, then you're going to do the epsilon delta definition. And here's the way this works. There's two pieces to this. And in terms of like showing this on your homework or doing it on the test, they're worth equal amounts of weight, okay? So if only you do the algebra portion of it, at least you've gotten something, but you're only going to get half of the material's credit because you've only done half the problem. So the way this works is you take the 3x plus 2 and you take away, so you subtract the limit value. So in this case, that's minus -4, and you put it in absolute values. Okay, so whatever the limit is, you're going to be putting it after, like with subtraction, the function value inside of the absolute values, and you set it to be less than epsilon. Okay, that's exactly what we did on the first problem. And then you're going to do some algebra cleanup on the inside. When they're linear, they work out really nicely. I will be doing one that's not linear in a moment, but this is 3x minus a -4 would be +4, so this is +6, less than epsilon. What can I factor out? A 3, so I'm going to just put it out in front. It is positive, so I don't have to worry about my signs. I can sort of check mark that this is reasonable because what I'm getting right here is matching what's underneath here. Sorry, that yellow was not a good choice, but x plus 2 is exactly x minus -2, which is what I'm supposed to be getting here in a moment, and I did. Okay, so that part matches, and then I can divide by my 3. So x, I'm going to write minus -2 just so that you can see it on there, but if you want to leave it as +2, that's fine. Epsilon over 3. This is half the work. Okay, the limit parts work too, but I mean in terms of the proof itself, this is half of the proof. You have found the delta value. Okay, it's just what we call the value at the end. It's called delta. And here's the way that we finish this out. So we've found all the pieces that we need at this point to be able to write the proof. And the proof actually mirrors this definition. All right? So they kind of go hand in hand. If you will memorize the one, you'll be able to write the proof for the other pretty easily. So it looks something like this. We know that the limit as x approaches negative 2 of 3x plus 2 is equal to negative 4 because for every epsilon greater than 0, there exists delta equal to epsilon over 3. That's the delta we found. Okay? Delta equal to epsilon over 3. Such that when, and now sometimes people get this backwards, we write the next pieces going upward, such that when the absolute value of x, you can put minus negative 2 or x plus 2, is less than epsilon over 3, right? When we're close enough on the x-axis, we are guaranteed to be close enough on the y-axis. So such that when x plus 2 is less than epsilon, then the absolute value of 3x plus 2 minus negative 4, you could put plus 4, is less than epsilon. That's the proof. The proof takes all the pieces that we worked hard to find and writes it coherently. In mathematical language anyway, right? But what it's still really saying is if we get close enough on the x-axis, we are guaranteed to be close enough to whatever it is we're looking for on the y-axis. Okay, ready for the next one? You have seen two examples now of linear ones, right? So we're going to shift gears and I'm going to do one that's quadratic. I did promise you that I would show you one where you could look at it graphically. If you don't like the graphical I'm about to show you, you could go back to doing it numerical. It wouldn't hurt anything. But this one is going to have x squared minus 3. It actually doesn't give us L. We are going to have to find L. So I said we'd do it graphically, so we will. We're going to put this graph into, or this equation into our calculator. You know approximately what it looks like though, right? This is a graph of a parabola. Audience participation time. It's a parabola. It's opening how? Upward, thank you. And it has a y-intercept of negative 3. So roughly speaking, the graph looks like that, right? It looks something like this. It's telling us we want to get close to x equal to 2, okay? So take a look at your calculator. My window is just set, I put it in as, x squared minus 3 into y1. My graph actually is set to a standard 10 by 10 window with negative 10 to 10, negative 10 by 10 to 10. I guess it's a 20 by 20 window, and I'm just going to trace along the graph. So I'm just going to hit the trace button. And as I trace, I want my x value to get close to 2. Now, as you get close to 2, you may not be satisfied with the number that's coming out. You might be like, well, it's not getting close to 2 close enough that I can really tell. If that's the case, just zoom in. You hit the zoom number 2 and zoom in a little bit more. And again, trace. And get close to the x value of 2. You can zoom in again, right? You can keep zooming in until you're convinced that the x value that you're getting when you're getting close to x equals 2 really is giving you what you believe to be the y value. What does it seem to be?
1.
Seems to be 1. Okay? Now, from an algebraic perspective, and in section 1.3, that makes sense. What happens if you put in 2 for x here? 2 squared minus 3 is 1, so that makes sense that that would be the value. So as you're doing this for your homework, you need to justify the limit on each problem. You can justify it with a graph if you'd like. You can justify it with a table if you'd like. Those are your only 2 options right now. That will be part of what you're looking to do when you do your homework, okay? You're going to have to do a graph or a table to just justify that when you're getting close to 2, I'll mark it here, that this point right here that you're getting close to is approximately 1. Okay? This is enough, as far as I'm concerned, to justify it from a graph. And then, of course, the tables looked like that, or the problem before. If you did tables on this problem, you'd be getting close to the x value of 2. So you'd be doing 1.9, 1.99, 2.01, 2.01, and so forth. Okay, is everybody good? Okay. Quadratics are a little trickier. They start out the same way. So we have actually, this is now equal to 1. So this is where we are. And we're going to take the absolute value of x squared minus 3, because that's what it says. We're going to subtract, I'll put that in parentheses just for clarity, and then we're going to subtract the value of 1, and we're going to make it less than epsilon. Every problem is going to start out that way. The equation or the expression that we're given minus the limit that we found in absolute values less than epsilon. Here's the problem. X squared minus 4. I can't just factor out 5 or a 3 like before, right? I don't have an equation that's like that. It's just not. So, or expression that's like that. But I can factor it. Okay? There won't be any confusing, complicated factoring. This is not algebra 3 on steroids, okay? Because we're not doing that. X squared minus 4 is something you should be able to factor without question. How does x squared minus 4 factor? Right. And the verbal description of what that is difference of squares. That might ring a bell. One of those matches what we want above. This is what we want. We want x to approach 2. So if we want x to approach 2, then the ending result that we're looking for down here is x minus 2 is less than something. That's where we want to end. Does that make sense? So the part that we really don't want to be there is the x plus 2. Agreed? Okay. What you can't do is divide x plus 2 to the other side. The reason you can't is because what's supposed to be on the other side is supposed to be a number, and x plus 2 is a variable. Remember, epsilon's a number. We don't know what the value is, but it is a number. X is a variable. I can't divide x plus 2 to the other side. So here's what we do. We say the following. Let x be a value. That's not spaced well. Close to 2, which we know it's supposed to be. That's the whole point, is that x is supposed to be close to 2 when we're done. And we're just going to make it within 1. Say 1 is less than x is less than 3. We're just going to go 1 on either side. Okay, so between 1 and 3. If you wanted to make it closer, you could. But, you know, whole numbers are nice, so I'm going to go with the whole numbers, between 1 and 3. Okay? And then I need to make this smaller. We're going to choose, whoops, how did I write it? The maximum value, we'll say it that way. Choose the maximum value, hence 3. So right now we have an absolute value of x plus 2 that's causing us problems, right? We're going to let x be the biggest value that we could get it, that we can let it be from the interval we picked, so 3. And we will get 5 if we do. Okay, so here's why we're choosing it to be the maximum value. What we're going to do eventually is replace the x plus 2 in the inequality by the number 5. The reason I want to replace it by 5 as opposed to saying let's let x be the number 1 and we get a 3 is because if I let it be 5 and I divide by 5, my interval is tighter and smaller than if I only divided by 3, right? Because 1/5 is a smaller distance away than 1/3 is. That's why we're picking the biggest thing, is so that we can have the smallest error. Right? We're minimizing our error. So we're choosing this maximum value. So the absolute value of x plus 2 times the absolute value of x minus 2 less than epsilon. There we go. And I end up getting 5 here because of the choice that I made. And if I divide by 5, I've got another epsilon over 5 here. I promise it's not always epsilon over 5. The last one was epsilon over 3. If you had decided you didn't want to go from 1 to 3 and you wanted to go from 1.5 to 2.5, that's fine. You would just let 2.5 be your number, and you'd put 2.5 in for x. You'd get 2.5 plus 2 is 4.5, and we'd be dividing by 4.5. That'd be fine. It's just kind of awkward looking to divide by decimals sometimes, so whole numbers are kind of a little prettier. And again, it actually made it a little bit tighter. We don't want to just be arbitrarily big. The whole point is we're supposed to be close. So we don't want to say, let's just let x be the biggest number possible. Well, that's silly, right? Like the goal is to be close to the x value of 2. So that's why we chose the 1 and 3. All right, this is the delta that I'm looking for. So now we're going to write out our proof. The formatting for the proof is always the same. The words are always the same. We know that the limit as x approaches 2 of x squared minus 3 equals 1. Because for every epsilon greater than 0, there exists delta, and we have to identify what we found delta to be, epsilon over 5, such that, and we want to talk about what happens on the x-axis first, such that when the absolute value of x minus 2 is less than epsilon over 5, then, going back upwards in our inequality, we are guaranteed at that point that the x squared minus 3 minus the 1 will be less than epsilon. So as you do your homework, it will always have 3 parts. They're right here. You're going to show somehow what the limit is, either numerical, that's a table, or graphical. We're going to actually draw the graph from the calculator. 2, you're going to do all of the algebra. You're going to have 2 that are linear and 2 that are quadratic. And then step 3 is you're going to write the proof out in this format.